In the previous two parts, we've looked at the H8, an initial evaluation of the H9 terminal, and I managed to get the H8 running by changing over to the 16K RAM card. In this part 3, we're going to look at a bit more detail of the RAM fault on the cards and how it's detected, and try and decide what to do to get them going, and that includes both the 16K and the 4K card. And we're going to switch our attention to what has proved to be an extensive bit of work to get the H85 serial port card running, which is needed for the cassette tape interface and the H9 terminal to connect up using one of the two ports. So let's see how we were doing on the RAM card and getting that going. It is jumpered here at the 8K spot, which is the 040000 address on the memory map. Obviously I've now got a 16K memory card at that address, so hopefully we can get this moved out of the way so we can test it. My plan is to put it at the 48K point, because if I put it at the 32K point, it'll be after the 16K RAM card and could be detected, and it'll try and put the stack there and it'll probably fail. I'm hoping the boot routine, I haven't really looked at it, but I'm hoping that doesn't actually check for non-contiguous RAM, in which case hopefully at the 48K boundary 260 octal high byte, we should be able to easily test the RAM with the RAM test routine using what we know is now the working 16K RAM. It's highly likely the top end of the 16K is working, even though I haven't tested it, because of course the stack works in it. So I have actually got the assembly manual for the 16K static memory board, but it shouldn't really hopefully need it, but it has got some diagnostic tools on it for us to be able to look at the system when it is running. So I've so far I have changed out the I'm wrong, actually the 48K is the 300 high octal byte. So what have I done so far on the card? I've put a new 74LS240 in 3 of the buffer positions. One of the something was taking the bus down, so I'm still not sure, so I've left those new ones in there as they're no good. There is a warning in here that this one, IC123, is on the online copy of the package, IC123 is a 74S240. Well, maybe it wasn't on this board. I'll swap it back over anyway, because I just swapped it out now for a 74S240, thinking it was supposed to be that, but it looks like my copy doesn't have to be. Don't know why. We'll take a look at why that might have been the case, what the difference is on the circuit when we look at the circuit diagram for it, which I've now found, because I don't have the circuit diagram parts of the book. I'll look into that and we'll update the video with why. So I must remember to swap that chip back over. I'm suspecting one of the RAMs is faulty. Hopefully not all of them are done, and we should be able to pick up the video on the testing for that. So let's get rid of this memory link at the 8K board, and then we'll stick it up at the 48K. So hopefully coming out. There we go. So hopefully that link will come out. Yep, there we go. Now we can put the link back in at the 48K boundary. I was going to try and arrange dip switches, but actually the pinout is not a DIL standard pinout, so you can't actually use a standard switch set, so I'll just have to swap the link over when I'm ready to go back to putting the card somewhere else. Should really have my glasses on to do this, shouldn't I? Typically we can use the tools we have available. There we go, it's taken. And so's that. There we go. Okay, so let's discharge any static from wandering around the house. I've also got all the 74 LS chips tipped out. I was looking at the dates and working out why there was a LS240, so we need to swap that over for another good LS. I'm not working with the actual memory chips, but out of circuit, worth keeping yourself grounded. I haven't got a ground map down here. Of course, I've had to move the whole thing to on the table because it's all so big you won't fit on the soldering bench you just saw, or on my desk where I work. So it's spreading out around the house on this project. It's a bit awkward, this IC2 123, because 123 because it's right next to that capacitor. Fold. We know that is a good working 240, and we'll take one of the known good ones just because we don't want to okay. I will swap back in the others once I finish cleaning all the legs off. I think you can see they are suffering quite badly with the old chip rot. Yeah, it's not very pleasant, and of course the single wipe socket, so it's inside. That's important to keep clean as well. So I will clean all the legs off. So, if anyone's got any suggestions about the best way to perhaps chemically treat those legs without damaging the plastic so that they don't deteriorate further, I'd appreciate it. Maybe you can drop it down in the comments below. I do read all the comments, and it is appreciated. So okay, now in theory we should be able to bang this in. I've moved the cards down, as you may be able to see. I've moved the 16K RAM card. I haven't moved the processor card to its P2 slot, so it's still on its little extender wire I made, but I have put the front panel bus connector, jumpered bus connectors into its P1 connector, and the processor does fit in the P2, but when I actually had the board, the machine rather, the processor was in the P3 slot, so I don't know whether the previous owner had started making an attempt to diagnose the faults on it. We shall see. Anyway, so now this board in here, which is normally where the I/O card goes, but it should give me enough space to check it. I've got to be really careful, don't bend these pins. They are quite there you go. You can see there's like a black plastic separator that ensures the slot in the bus, so you don't get the offset slightly, which of course will destroy the whole machine. So I think we'll put it level so we can use it better before we power it up. So I'll reset the camera shot and we'll have a look. Right, so acid tester turn on. See if we get a howling mess again. No, luckily it still boots okay, so the card is not corrupting the bus. So we obviously the LS chips that were doing it to the card address, which is 300. 000. That should be the first address on the card that we have put at the 48K boundary, which is the 300 000. So if I write a value into that memory address, if I alter it and put 000 in, now we're at a drag, go back to that previous address, we've got a 0 in it. So it took the value. Let's try putting 277 in, which is 555, I think. Yep, it took it. Okay, well that's interesting. So the bottom end of the 4K RAM board is working. Obviously I made a mistake earlier. The top end of a byte in octal is 377, not 277. So, but it does take that as well, as you can see. So that's the first address. Let's put it in, and we can put it into each of them. And it will stick. So all 8 bits are running. Okay. Alright, so it might be more subtle memory error when you may need more detailed memory testing. I punched the memory test routine back in with some slight changes. I've changed the start address to ensure it tests from 300 all the way up to the end address. So it will go from 300,000 up to 320,377, which should mean it'll stop at 320, I would have thought, because it will fail because there is no actual memory address there. I should try and stop a little bit earlier, but the idea was to find the first non-existent memory address. So we've set the PC counter to that, so now we want to display the BC register, which is the value being written, and we can hit go, and it'll beep and show us what it couldn't. So 001, if we press the register button, and HL, then HL gives us an address of 303,313. We go to mem and try to go to 303,312. Now it has a value of 1 in there, so if I alter that and write 377 and go back, it only got 277. So at this point you can think, yep, bit 7's faulty because we've got a bit that wasn't right. It's actually rather more complex. I've taken out quite a lot of footage of trying to work through what's causing the memory failures. It actually needs a bit more diagnostics, which you'll see after. But I did take a look at the way the test routine works, because that was showing the fault up where writing in by hand wasn't showing the same effect. Probably because of the way it's doing the memory access, maybe. The test routine, I think there's an increment. Of course, this could show up problems on the memory. Yeah, 0 byte at the end. Load it. Increment the next value. Increment location. Yes, it increments the HL and the M address, which is the HL register pair, directly. So it's just doing an increment on the address. So it's incremented the address, read the address, contents, added 1 to it, and then gets the value back. Some head scratching needed here. So reading the troubleshooting manual, it reckons if you can write the value back, which we can, that's likely an addressing error on the board. So maybe one of the RAM chips is responding incorrectly to an address, assuming the address decoder is actually decoding correctly and triggering the selectors. So I could cram the cards up a bit further and then leave the RAM available to see with the scope. What we need is one of those little extender cards that I've seen being sold incredibly rarely on eBay. Maybe we need to get one of those for diagnosis purposes to pull the card out. Would be quite nice to own, I think. I'm going to try and juggle the cards a little bit so that I can bring them a bit forward, so that I can have more space to look at the 4K RAM card and maybe look at the chip select lines on each RAM and see if they're being selected. So this is the chip select line as seen here on the 4K link wire, which basically is common across all the chips on the particular bank. And in fact then we are going to be looking at the data coming out of pin 7 when that chip is selected. What I've done is I've set address 300,000 to all zeros and the address 1 to be all ones, 377. So if I go into pin 7 now on the first IC, which is 117, there we go, we're not seeing anything, it's a 0, which is correct. So if I go to next address, it's a 1, which I think, as it's a MOS chip, is just under 3 volts is probably likely. And if I go back, it goes back to 0, so that's what we'd expect. Now if I go to IC116, oops, which is already showing a 1 because we're there, and Now interestingly, at 0 you've got that little peak there of almost as high a voltage. I'm not completely convinced that's enough to drop it below the 0 line. IC115, then this is the 1, which is correct, and we get a nice clean 0. We do the same then with the, and you can already see on the 0 byte IC114, it goes to a clean 1, it doesn't. So I'm suspecting 116 and 114 are not functioning correctly. It might be too short, it can't be seen, but it's certainly not a very good thing to be turning some data onto the bus when it isn't a value you should be getting. But I certainly suspect it's faulty RAM chips. So we'll have to order some spares and replace them. So that took a little bit longer than we thought to work out what the actual fault was, including a lot more swapping of chips. I did a lot of in and R-in and silences, which you haven't had to suffer in the video. So I decided, luckily enough, on eBay they actually had a seller listing the TMS 40L 4425 static RAMs, 4K by 1, which is what is needed on this card. And I was reasonably confident that there were 2 definitely dud in the bank of 8 that you need. So I ordered 10, which would allow me to repair the 2 broken ones, and also to upgrade the card to its full 8K should I decide to add the sockets. So it was off to wait for those. The testing for the 16K RAM card did prove there was a fault in the upper section of the memory. I've drawn a little diagram here which you can see shows the area where I put the 4K RAM card at the top area of memory when I was testing it. So it's a little bit clearer. Hopefully you can see it starts with the PAM monitor in the lower section. We'll come on to where the floppy drive controller has some memory on it as well, which sits down in that section. Then you've got the sort of 8K boundary, the 04000, which is where things start. That's where the 16K RAM card is. And there was I've scribbled over the bit that was actually faulty in the 16K RAM card. There's several cells showed up as errors. I didn't really try and work out which of those 8 chips was faulty. It was a bit more work than I wanted to undertake at the time. And again, luckily there was a seller this time in France. The previous one was in Switzerland, I think, that was selling the MK4104 4K by 1, although they're both 4K by 1, they're slightly different pinouts. So I ordered 8 of those, intended to replace the whole bank, thinking that the card looks quite nice with the gold ceramics. I can probably just add in one bank, won't look quite so bad. We'll have a couple of spare ceramics then in case any go faulty on the other areas of the chip of the card. So that's where we are. It wasn't cheap, I'm afraid. Those RAMs come in about £4 or £5 each, so we're, just that set is going to be nearly 60 something pounds worth of memory to repair this. It's not a cheap option doing this sort of work, and I couldn't, unfortunately, as I say, get the gold ceramic chips, so they will be plastic package ones for the card, but at least it'll be working, and that's, I think, really important for machines, that they work. They are, museum quality, yes, but they should still work. So that's where we are. This video we're going to take an initial look at the H85 card, as I promised, but that turned into a bit of a nightmare, and we even had to break out the big guns of the logic analyzers, both the 8-channel and the big HP, which I'm sure one of my viewers at least has been waiting to see come up on the channel, because I bought it off of him some time ago. So we'll see how this goes, and we'll pick up then later. Okay, we're back with the Heathkit H8, looking at the H85 serial I/O card, trying to get that working so that we can actually see some data. The problem seems to be I'm seeing no data out. As you know, we remove, or maybe you haven't yet on the video, I removed IC122, which is the 74SOO that actually provides the connections to the TX and RX. That's following an idea on the user group forum, Google group, and good idea. Was something I was thinking of doing, is just to take that as a 5V TTL. So I've got my 5V TTL connector, and the one I use pretty much on everything is now plugged into the relevant port. So I've got one in pin 7, which is the ground, and I've got a lead in pin 9, which should in theory be one of the, that's the data out, so that's on the blue, and then I've got a data in on pin 11, which is the incoming port, and that is now on the chip that's been removed. That chip does have a presence as well on the DTR line, but we're not using that, so that transistor on the input line from the multi-port connector at the back is just remaining unused. So I've swapped the LS buffers, as you will know, because there's probably a close-up of that, which is basically the legs have fallen off on both sides now, and then they're falling off quite badly. That might have been aggressive testing maybe in the tester, or just pulling it out of the board, but they got new LS 240s in there. It's usually just a good idea to get a known baseline of working buffers. Okay, we are at that position where I've not really made a lot more progress since. I suppose I've just ought to check that the actual machine still boots okay. Yes, it does. So that's a good start. In the manual, there is a fairly good description of how the system works, based on the block diagram that's available. I'll probably put up a better copy of that in the corner. But essentially I'm just going to be looking at this section here, which is going to be the make sure I'm getting data in, obviously the USART for the serial I/O card, and I'll need to make sure the address decoder is selecting it. I'm going to ignore the cassette side of the card for the moment. I have already checked the data scaler rate, but I might just check the frequencies to make sure they're okay, because I have set the TX and RX clock to be 9.6K, which will be a bit faster to talk to, although I've made that a jumper so we can put it down to 600 to put the H9 back on when we're ready to go. So let's see if we can get as far as we were in the manual, which was doing some testing with the setting the USART ports up. There's a couple of little quick instructions which are for testing the machine. Just before here we are, so we've got on page 41, and it's basically in order to test the output, it's going to put it into a serial output mode that allows us to actually transmit in async. And in theory then that should be connected out, as I said, to the connector in pin 9, which is the blue one. So we should be able to see data out on the blue line. Now whether that's the correct connector for me or not, I don't know. So not sure whether the scope's in view. Maybe I can move it over a little bit. Move the calculator out of the way. Hopefully you can see the calculator in the, yeah, so you can see it all now. Yeah, so you can see the scope as well as me. So that's the final output part of the port, which is about 3.5 volts is holding, which is, as we'd expect, to be held high. So if we make sure it's reset, go what it is. So press the mem key, and now we want 316373, and that is now going to be the out key to put that out onto the select port. Now I suppose I ought to at least see if the chip select is triggering on that as well, didn't I? So what we need is a good earth connection elsewhere on the board, perhaps. Maybe we can do that here. Means that we got a ground. I can use the other as a probe then. Okay, so yeah, blue C in it. So we should, when we press that out, we should see on the circuit, we should be seeing a chip select happening, which will be coming in through this various circuitry, but it's basically going to come through this port interchange switch, and it should happen to be on the chip select on pin 11 of IC124, which is the one we're interested in. It'll be on the other one as well, but we're not worried about that at the moment. So IC124 is the bottom one, of course, harder to get at, and I said it was pin 11. Okay, so when I press the out button, that should do a chip select. Why is that not happening then? It might well be that I don't have triggering on the second. So yeah, this definitely, so if we trigger on channel 2 and put ourselves into a single normal mode, then whenever we get a select, we should start to see it. There we go. So we are seeing the chip select regularly, which I assume is maybe the monitor generating that. Let's reset completely and stop. No, the chip select happens all the time. Okay. That's probably not correct. Why is that chip being selected at that point? Okay, let's look a little bit earlier maybe. Okay, well, of course, the chip select will pulse if that lower address A7 to A1 are pulse into any address that uses it, which they will be several times. But of course, the actual buffer gate and the buffers onto the bus are gated with a couple more AND gates that actually look at the other signals in terms of I/O read, I/O write. So what we need to do is we need to have a little look and see if the buffer switch is being selected, which is actually pin 8 on 118, IC118, pin 8. Assume that is 118 at the very bottom there, can't quite see. I might go and get some clips actually rather than trying to hold them on. So if we put in our port select, so 373, and I press out, we do not see a chip select or buffer enable. Okay. Do it again. No, nothing. All right. So we could have a problem in the address decoder circuitry, maybe. We'll come back on it afterwards.